And all the probability distributions that we have looked at, the actual probability distribution has been given. Your book says in the real world there are very few instances in which the probability distribution is conveniently available. Substantial effort is usually required to obtain the probability distribution. Probabilities are determined by using the techniques that we went over in Chapter 6. It says, sometimes, however, you get lucky. The random variable you wish to analyze either conforms to or can be approximated by an experiment that has a known probability distribution. 4 well-discrete distributions that we're going to discuss are uniform, binomial, Poisson, and hypergeometric. Uniform distribution is pretty easy to understand. Binomial is probably, I've seen used the most, not that the others aren't important. The Poisson and hypergeometric distributions, we may have to do a little something that some of you have never done. We may have to deal with the exponential function e to the x a little bit. If you've ever heard of e to the x, which if you've taken college algebra, you have. Some of you are like, why do we have to know this whenever you're in college algebra? And then you'd never really get to use it, maybe until you get into your junior, senior level class. But you're in luck. You'll actually be able to use it to find some type of real world information in here whenever we go over Poisson distributions. So you'll see what I'm talking about. So those are the 4 types of distributions that we're going to cover. Probably the easiest one to understand is the discrete uniform distribution. Think about what uniform has meant as we have, when we were looking at sets of data. We were looking at sets of data and there was a question on a test that was, how is this data distributed? And I believe one of the answers was it had a uniform distribution. If you think about histograms that could represent sets of data, it's uniform if they're all relatively the same height. So a discrete uniform distribution, your book says, is one of the simplest probability distributions. Each value of the random variable is assigned identical probabilities. There are many situations in which the discrete uniform distribution arises. So if you have equally likely outcomes, then that would be a discrete, you could form a discrete uniform distribution, such as rolling a die, tossing a coin, things like that. So the table is given again about throwing a die, where you can see each probability is the same. Then your book goes through another example. It says, suppose a purchasing agent has just received a pricing and delivering schedule from a new vendor. The delivery schedule was quoted as 1 to 4 weeks. The purchasing agent then subjectively constructs the following probability distribution for the time to deliver, or the time to delivery. The probabilities of the random variable are given. All right, and so each week has the same probability. So you see The probability it will be delivered week 1 is the same as the probability it will be delivered week 2, is the same as the probability it will be delivered week 3, is the same as the probability it will be delivered week 4. They're all 1/4. If those probabilities were different, this would not be a uniform probability distribution. But they are. And so it's really easy to understand what a uniform distribution is. All the probabilities are the same. So maybe you can think of other instances. I guess going back to the roulette wheel, the probability is the same for every slot. It's just random. So you could make up a uniform distribution, a discrete uniform distribution that, let's say, I think some roulette wheels have 38 slots. You could number it, whatever numbers they are. You know, it's probably 0, 00, then 1 through 36. And for each one, you'd have a probability of 1 out of 38. So that would be a uniform probability distribution. You know, or let's say that we took a deck of cards, 52 cards. Each card in the deck is unique. You know, there's 4 suits, there's 13 cards in each suit. If I was to shuffle a deck and then randomly select one card, the probability of me getting that card is 1 out of 52. You know, there are not 2 6 of hearts in the deck. There's only 1 6 of hearts. So the probability of me drawing a 6 of hearts is 1 out of 52. I could list a discrete uniform distribution. If I wrote down every card, you know, the number and the suit, then the probability of getting each one is 1 out of 52. Of course, the sum of all those probabilities would be 1. And since the probability is the same, it is a discrete uniform distribution. All right, enough about the easiest type of distribution. Let's, usually when students get to this next section, they kind of spaz out a little bit because it's a little bit more math than maybe we've been doing, because it's a different formula. Okay, one of the most commonly used distributions, I'd say the most popular that we'll cover, is the binomial distribution. So this is a very big topic for this chapter. All right. Now, binomial. The word bi means 2, right? So a binomial distribution will arise whenever you have some experiment where there are 2 outcomes. All right? So they arise from experiments where you have 2 outcomes. Maybe something like, maybe a product is defective or a product is not defective. They don't have to have the same probability, but there are just 2 outcomes. True-false test. Something's true or something's false. Your book says something about, in the business world, these are rather common. Maybe in a market research, a survey respondent will either recognize a company's brand, or will not. I've done little surveys like that. I think I've told you about something that I've done through Amazon before, just to make spare change on the side. It's called, I think, turking is what I told you it was. And so a lot of times, you know, I've done a survey where it'll say, do you recognize this product? Or show you a picture and then, what product did you recognize? Which one was the most appealing? You know, things like that. So, believe it or not, the colors that are used in marketing are important. Think about the colors that are used at McDonald's, that are used at Wendy's, that are used at Arby's, that are used at Hardee's. You know, a lot of those have reds in there, and they're there for a reason. There's a reason why they're not pink and purple polka dots. You know, that color is more appealing, and studies have shown that it is. That's why they stick with those colors. Let's see. So with a binomial distribution, we do have certain characteristics that we have to go by for a binomial experiment. All right. So a binomial experiment is a random experiment which satisfies all of the following conditions. There are only two outcomes on each trial. One of the outcomes is usually referred to as a success. The other outcome is a failure. N would represent the number of identical trials. The probability of success on any one trial is denoted as P. So P, lowercase p, that's going to be the probability of success. Now, your book here does something different from other textbooks that I've used. Generally, if you look up a binomial probability distribution, you look up the formula, you may see the failure written as what it has in your book, but I would be willing to bet that more times than not, you'll see it written another way. Anyway, it says the probability of failure is 1 minus p. Now, I've seen 1 minus p written as q a lot. So if you look up this formula in a different book, or maybe down the road you are in another class and you go over a binomial probability distribution, know that if you see q for failure, that's pretty standard. Your book, however, writes failure as 1 minus p, which means the same thing, because the probability of success plus the probability of failure has to be equal to 1 for anything. Okay? So that would mean that Q, which I told you in some books is failure, would be equal to 1 minus p if you subtracted p from both sides of that equation. So while your book uses this, don't be surprised if you look up a video or you find something different. You'll find Q written instead of 1 minus p. And your book is pretty consistent. Every time, every formula that you use, that I would use Q in from my prior knowledge, it puts 1 minus p. So as long as it's consistent, I'm fine with that. If I mistakenly say Q, you should know I'm talking about the probability of failure, but I'll try not to do that. All right. The probability of success and the probability of failure does not change from trial to trial. It's the same. I talked about a defective product or a non-defective product. You know, if I go and I select 100 tires, it's going to be the same probability that I get a bad tire in each set of 100 that I take. That probability is not going to change. All right. The trials are independent. So what does that mean? They do not depend on each other. You know, just because I get a success on this trial doesn't mean I'll get a failure on the next trial or a success on the next trial. They're all independent. The binomial random variable is the count of the number of successes in n trials. The binomial random variable is the count of the number of successes in n trials. All right. So I'm really interested to see on your formula sheet if I can pull that up, what is given. That's right. All right, so the probability distribution formula is this formula here. It looks a little confusing. I guess binomial probability distribution. Remember, this first part here, this C with the X here and the N here, that's the combination. So to figure out this part, you have to say N factorial divided by N minus X factorial times X factorial. All right, so since these variables are written as a string of variables, just in, with no signs in between, that of course that means multiply. And so we'll work that part out. Then we'll say that times, remember P is the probability of success. So we'll be given some percentage or some probability of success of an event occurring. So you'll have that, and then we'll raise it to the X power, which is the same as this X here, except it's not factorial. And then you have that times 1 minus P, which I told you some other books call Q, raised to the N minus X power. Okay, so you need to make sure that you understand how to use your power buttons on your calculator, because you're going to have to use them. Alright, so there's an example that's given in your book. It says roll a single die 4 times and record the number of sixes observed. Does the number of sixes rolled in 4 tosses of a die meet the conditions required of a binomial random variable? It says the experiment either produces a 6 or not. So there's a success, that's rolling a 6. There's a failure, that's not rolling a 6. Okay, so there are 6 outcomes, right? Alright, so it says roll the die 4 times. So N equals 4. What's the probability of getting a 6? The probability of getting a 6, that's going to be 1/6. So that is our P. Okay? What is the probability of not getting a 6? 1 minus P. Right? So if I want to know the probability for getting no 6, where the random variable is 0, that would mean getting no 6, right? Then I would have to say, okay, 4 trials, so I'm going to have 4 factorial divided by, what is that? 4 minus, how many times do we want to get a 6? 0 times 0 factorial. Remember, 0 factorial is defined as 1. So that doesn't divide by 0. I forgot my factorial sign there. So you end up with 4 factorial divided by 4 factorial. Okay, which is just going to be 1. So the first part here of our binomial probability distribution formula is just 1. For x equals 0. We get 1 times the probability of a success, that's 1/6, raised to the, how many times do we want to, for x equals 0, that means we don't want to get any 6. So that would be to the 0 power times 1 minus 1/6 to the n minus x power. That would be 4 minus 0 power, or 4. All right, so the probability of rolling a die 4 times and getting no 6 is going to be equal to this right here, whatever we get out. So that's going to be 1 times anything to the 0 power is 1, except possibly 0. So that would be 1 times, that's going to be 5/6 to the 4th power. Now if you work that out in your calculator and you round it to 4 places, you would get 0.4823. So that's the probability of rolling a die 4 times and getting exactly no 6s. Now we could do that for getting 1 6. We could do that for getting 2 6s. We could do that for getting 3 6s. We could do that for getting 4 6s. If we calculated all of those values, then I would be able to copy down a table with a binomial probability distribution, and all those probabilities are guaranteed to add up to 1.